right, so yesterday we ended up just talking about the equilibrium expression, and we talked about two kinds. Well, actually, we talked about 3 or 4, but the ones that we were focusing on was KEQ. And if we were talking about my favorite equation, then the equilibrium expression for this.
You did CD plus DD.
Okay, thank you. The equilibrium expression for this would be this. This was also called the law of mass action. We also decided that if you had all gaseous things going on here, you could find the equilibrium according to their partial pressures. And that we put into parentheses so we would remind ourselves that it's not a concentration, it's a pressure, yeah? Everybody recalls this bit and should have done most of their homework. Okay, now there's a way to mathematically correlate K, which is also called Kc, and also is K, to correlate this to the pressure, and the way that you do it is through this equation right here. Kp equals Kc times the quantity RT raised to the delta N. Now, this is on your green sheet, but it might not be on this year's green sheet. The way I always remember this is when I talk to you, I try to be politically correct. And that tells me the form of this equation, politically correct. So Kp is equal to Kc. R is the gas law constant, the one we are most familiar with, 0.0821 lat/molka. And T is temperature. Obviously, it must be in Kelvin if we're using R. And N is the difference in moles of gas products minus gas reactants. So I want you to ignore any moles of anything that is not a gas. Look at the equation. The coefficient is equal to the number of moles. Take the number of moles of gas in the products minus the number of moles of gas in the reactant, and you are good to go. If there is no difference, then Kp equals Kc. Good?
Mm-hmm.
All right. Okay. Kc equals Kp if the number of moles of gaseous products equal the number of moles of gaseous reactants. Here we go. The reaction for the formation of nitrosyl chloride, 2NO gas plus Cl2 gas, is in equilibrium with 2NOCl, which is also a gas. This was studied at 25 degrees C. The pressures at equilibrium were found to be these numbers. Calculate Kp for this reaction at 25 degrees C. Well, from this, the first thing I need to do is make sure it's balanced. It is. Then look at the states of matter. They're all gases, so I know all of these will be included in the equilibrium expression. Then I'm going to write the form of the expression. The partial pressure of NOCl raised to the second power times the partial pressure of NO squared times Cl2. So now I can add some numbers into that. NOCl times NO.
I thought Kp equaled Kc RT delta N.
We are just finding Kp, and they told us the pressure at equilibrium were this. So we're just going to find the equilibrium pressure, or the K value right now. Oops. 3.0 times 10 to the negative 1. When I do my math, doing my orders of operation, making sure I don't mess up, I find that Kp is equal to 1920. All right, Kp is equal to 1920. I would like you to look at this reaction and then this and tell me what is favored, the reactants or the products?
Products.
The products are, and that is borne out in the equilibrium pressures. There's a lot more of the product than there are of the reactants. Equilibrium lies to the right. Okay. Moving on. Using the value of Kp obtained in the previous exercise, Kp was 1920. Calculate the value of K at 25 degrees C for the reaction, same reaction. Let's recall Kp is equal to Kc, quantity RT raised to delta N. So R is our gas law constant. T is our temperature, which is 298. And our delta N would be the products minus the reactants. And I see we have 2 moles of gas, and we have 3 moles of gas here. So that is a total of -1. Delta N is -1. So substituting in 1920 is equal to Kc times the gas law constant times temperature raised to the -1 power. And I did my math in little baby steps. I think I got 1920 is equal to Kc 24.5 raised to the -1. And then 1920 is equal to 0.0408 Kc. Kc is equal to 47,058. No?
No, no. Put it back in.
All right.
Wait,
You're only
is the answer wrong?
Only 1,000 off? That's what I got, that's what they, what'd you guys get?
4,601.
Maybe I put something in there wrong. Close.
5%?
Oh, I don't know, I'm just so tired of being sick and tired. It's good for me. All right. All right, now I want to talk about something totally different. Are you ready? Totally different. Put your calculators down. Pay attention. When I was talking initially about these things, the values that go in here are the concentrations at equilibrium. Anytime you find K, you must use the equilibrium concentrations. Likewise, when I find K, I need the equilibrium pressures. Do you understand that? Anytime you use the law of mass action for K, EQ, or KP, these values must be the values once it reached equilibrium. So remember this graph from yesterday that looked like this?
Yeah.
And here was equilibrium was established after this point. These are the only values that can go into these expressions. Okay, now we're going to talk about something called the reaction quotient. And the reaction quotient is the same form, the law of mass action. The difference is the concentrations inside the brackets or the parentheses are not necessarily at equilibrium. They're given concentrations or pressures, and it's your job to determine whether those are the concentration and pressures of equilibrium or which way the numbers must shift to reach equilibrium. Hang on, here we go. So for the reaction quotient, the law of mass action is exactly the same. Q, which is the abbreviation for the reaction quotient, is equal to the products raised to their coefficients over the reactants raised to their coefficients. Looks like K, but these numbers could be a little sketchy. You don't know. Now, if the value, the numerical value, is less than the value of K, then the system is not at equilibrium. If Q is a smaller number, that means that this is too small while this is too large. This is too small while this is too large. In order for the reaction to get to equilibrium, which it will, you'd have to shift to the right. Reactants would have to be made so this value got bigger, which would force this value to get smaller. Are you good there? Hang on, I can make it easier. Wait. If Q equals K, you're at equilibrium. If Q is larger than K, that means this is too big and this is too small. And in order to get to equilibrium, it will make more of this, which will make less of this, making the value of Q closer to K's numerical value. You know what? This drove me nuts. There was way too many if, then, what should I do? I don't like this. So that segued into the next page. Here it is, a memory hook. Put the number on a number line and then draw a line from Q to K. It will tell you the line is in the direction that the reaction will shift to establish equilibrium. So here is our reaction. Okay, read this right now.
Why is it so big?
Get over it. Okay, that's why it's so big. Everything is a little text box, and I just didn't want to mess with it. Okay, let's do some pretend scenarios. Let's say that we were given some concentration, and we found Q is 123. And we looked up the equilibrium constant for this reaction, and we saw that the equilibrium constant is 456. All you do is put it on a number line. Look, 456 is over here. That's K. Q is over here. Q is over here. It's 1, 2, 3. In order to reach equilibrium, it will have to shift to the right. What will have to shift to the right? This will. You'll have to make more of this, which will use up some of this. Got it?
So
And then it'll get itself to equilibrium. The goal is that what the values you're given are going to eventually get to equilibrium. Your job is to figure out, does that mean making more product or does that mean making more reactants? Obviously, in this case, that means making more products. Thank you very much.
So you just increase the coefficients?
No, you cannot increase the coefficients. What happens is you have to allow it to,
Go longer. Right,
Yeah.
it's like the
Yeah.
time that it's taking the reaction,
Right.
you're saying it's
You're not there yet.
carrying on.
yeah, you're not there. What is happening, if we were looking at the graph for this particular one, we would need more of this to form more of that. You're not at equilibrium yet. Get it? Okay, thank you very much. Now, let's say that Q is equal to 0.123. And K is equal to 0.456. We're just going to put it on a number line. Wait, did I do that backwards? Indeed, no, I didn't. Yes, I did. Okay, now everything's fine. So, here is K, here is Q. In order to reach equilibrium, we need to shift towards the left side of our reaction. I need more of this. I need more of this. Got it? Okay. Here we go. Using the reaction quotient. For the synthesis of ammonia at 500 degrees C, The equilibrium constant is 6.0 times 10 to the negative second. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. K is equal to 6.0 times 10 to the negative second. Here are our concentrations. What are we lacking? A balanced equation. And you need to know, we use the synthesis or the decomposition of ammonia all the time in equilibrium problems. So just learn it now. N2 plus H2 yields NH3. And it's our job to see if we're at a double-headed arrow or not. Balance this bad boy. Okay. And now we can write the value for Q. Q is equal to NH3 raised to the second power times N2 and H2 cubed. Putting some numbers in there, NH3 is 1.0 times 10 to the negative third over N2. All right, I'd like to see that you get the right answer, so do this. Which way? Okay, and then I have to do this because this is left. My left hand makes an L.
That doesn't help people with dyslexia.
I am dyslexic, that's why I do that. L. I got a giant number.
It's
I got,
12,500,000.
Yeah, I got Q equal to 1.25 times 10 to the 7.
I did definitely imagine.
Okay, now on a number line,
That's gonna be huge.
here is K, which is 6.0 times 10 to the negative 2. I do not have enough paper to put this to scale, but Q is in the next building. It has to shift left. It's not even close to being at equilibrium, correct?
Correct.
Correct. It's not a double sum here. Okay. For using the numbers in B, I said that Q is equal to 0.060. That is equal to 6.0 times 10 to the negative second, correct? K equals Q. These are the equilibrium concentrations. Hang on. For this one, I said that Q is equal to 0.002. Here is 0.002. Here is 0.06. It must shift to the right. Good?